Good afternoon, everyone. This is College Algebra at College of the Sequoias in spring 2020. We're in our COVID-19 lockdown and lessons must go on. So this is chapter 4. We're working on exponential functions and logarithms. 4.2 is on the exponential functions. So let's just take a look at them and what an exponential function is. What makes a function an exponential function? Exactly this. Exponential functions have the variable in the exponent. In the exponent. And they're often in the form, well, they are in the form f of x equals a to the x. We put some stipulations on a. We don't want a to be 1 because 1 to any power is 1, and it's boring. It's a waste of time. It's not even a function. It's a constant at that point. And we want a to be greater than 0. If it's less than 0, it starts bouncing depending on what the variable is, and that gets a little bit ugly. The domain for these functions, so let's take a look at it. We've got a positive number here, like say 2 to the x. It doesn't matter what I put in. If x is negative, we have 2 to a negative exponent, but that just makes it 1 over 2 to the same exponent, which is a positive number. It gets really small, but it's positive. If x is bigger than 0, 2 to the x blows up really quick. So it turns out, even though we have a domain we can put anything in, the domain is all real numbers or negative infinity to infinity, our range is limited. In fact, it cannot ever even equal 0, so we have to use parentheses for the 0. It's always greater than 0. And we can take a look at 2 to the x right here. I've got it on Desmos right now. We can see to the left of y, when x is negative, this is 1. Let's make it where it looks like a 1. That's a 1. This is all a fraction, and it doesn't matter how far we go to the left, the red line is still above the black. It gets really close, but it's above it. Zoom back out. We have some other properties that must apply. So we'll come back to this example in a second. Let's go back to a. If we have a to the b power and it equals a to the c power, that can only be true if and only if b equals c. Which makes sense. If the bases match, the exponents match. This if and only if, you will see this frequently. It happens so much, especially when we get to calculus, we abbreviate it as IFF. If you see IFF, it means if and only if. If and only if means this is a two-way street. A to the b power equals a to the c power implies b equals c, and b equals c implies that a to the b power equals a to the c power. So if we look at values that are between 0 and 1, if 0 is less than a is less than 1, let's say, for example, a equals 1/2. I've got 1/2 to the b power. How does that let's compare these. Let's compare 1/2 to the second power to 1/2 to the third power. This ends up being 1/4, and the right one is 1/8. 1/4 is bigger, which means when a is a small number, this goes downhill. It's a decreasing function as x goes up. Because x equals 2 gave us 1/4. X equals 3 gave us 1/8. We can take a look at that. Not supposed to have a comma there. And look at that. It's now a decreasing function. So if a is greater than 1, what does it mean for in general? If a is greater than 1, and we're looking at f of x equals a to the x, then f of x is always increasing. And if a is between 0 and 1, we don't want it to be less than 0, or we don't want to be 0, even 0. We don't want it to be 0 either. Then f of x is always decreasing. We just showed that right now. And what does that tell you about exponentials? Any function that's always increasing or always decreasing has an inverse. That's what we looked at in 4.1. And when we get there, these are called logarithms. That'll be 4.3. All right. And what can we do to work with these? We can play around with them a little bit. They're not always the most exciting thing. Let's look at f of x equals 4 to the x power. We can evaluate them. We can plug in values for x, like f of 2 equals 4 to the second power, which means 4 times 4 is 16. F of 3, same thing, 4 cubed, 64. We can plug in negative exponents or negative values. That turns into 1 over 4 squared, which is 1 over 16, etc. We can even stick in fractions. 4 to the 1/2 power is the square root of 4, which is 2. Do I have 4 to the x in here? I don't. Let's make that look like 4 to the x real quick. So at x equals 1/2, right here, y equals 2. And that's what we just showed right here. We put in 1/2, we get 2 out. Good stuff. A fun fact you don't know or didn't necessarily know and it's interesting. Look at f of a equals a to the 5th power. If a is a single digit, f of a equals a to the 5th power ends in the same digit. Crazy, right? I'll point that out up here. 1 to the 5th power is 1. 2 squared, or 2 to the 5th power, is 32. What is 3 to the 3rd power? 243, I think. Or 3 to the 5th power is 243. 4 to the 5th power is 1024. Notice the ending digit matches the digit out here. Even 9 to the 5th power. Works for all of them. It's kind of neat. It's a fun fact. There's your Jeopardy question for the day. These solutions don't always have to make us happy. Like, let's go back and look at f of x equals 4 to the x power. What if we plug in 2/3? We have 4 to the 2/3 power. Well, that's the same thing as 4 squared to the 1/3 power. Remember us working and manipulating exponents in chapter 1 in the review section? This is 16 to the 3rd power, which is the cube root of 16. And if you throw that in a calculator to 2 decimal places, you get 2.52. It's not that friendly. But we can try to look at it here. 4 to the 2/3. Well, this is the 0.6 mark. So let's see. We're looking for 0.66. That's 2/3. There we go. 2.518. And if you have it like 0.667 is a little bit closer to it. And it gets to that 2.52-ish. So we can see it. It doesn't have to be a friendly number. It can be a decimal, an ending decimal. How do we go about graphing these by hand? Like when we started, we had this was 2 to the x. And how does that work? Well, let's graph them. Let's practice doing it by hand. And when you don't know how to do something, you should always go back to making a table. So we're going to plug in x values, and we'll get y equals 2 to the x spit out. And we often like to try -2, -1, 0, 1, and 2. So this says 2 to the -2 power. That equals 1/4. And we get the coordinate -2, 1/4. If we put -1 into the exponent, we get 2 to the -1, which is 1/2. We get -1, 1/2. We put 0 in the exponent. Anything to the 0 power is 1. We put in 1 and we'll put in 2. We get 2 and 4. In fact, you'll notice as you go through this, whatever you have here, the negative ones, these numbers right here, flip them over for the positive ones. That's a handy, a speeder up kind of thing. Let's look at 3 to the x real quick. How does it differ? Well, we can see they have similar shapes, and they both cross right here at 0 to 1. We'll do the same thing. This is 3 to the negative 2, 3 to the negative 1, 3 to the 0, 3 to the first power, and 3 to the second. This ends up being 1 over 9, 1 over 3, and 1. And these just flip over. In fact, it's easier to do the positive ones and then flip them over to get that. You'll notice we had 2 here. This is a 2, and that's a 2. And that's 0, 1. We had a 3 here. This is a 3, and that's a 3. And this coordinate in the middle is 0, 1. This is true for all f of x equals a to the x. If you want to plot it really quickly, you can do negative 1, 1 over a, 0, 1, and 1 comma a. It works every time. Now, if we switch it, if we change it up a little bit, what if we want our whole HK thing going on? This used to be our center. And if we think about what we did before, 0, 0 in old graphs got shifted to HK. How does that translate here? Well, we added h to 0, we added k to 0. Here we're going to add h to 0, we're going to add k to the 1. And that becomes our central point. That's the new center. And then you just do this shift to the left and right of it. So which one of these was blue and which one's red? Blue was the bigger A. Notice that to the left of 0, the bigger A is, the faster it goes to 0. To the right of 0, the quicker it blows up. It gets large faster than the other one. Like at x equals 2, 2 to the x is 4, but 3 to the second power is 9. It starts blowing up really quickly. Let's graph them. I'll leave those up there where we can see them. So we're going to do it by hand. We said the range can never be 0, which means 0 in general is our asymptote for the default graph. It's a horizontal asymptote. For y equals 2 to the x, we have a point at 0, 1, we have a point at 1, 2, and we have a point at negative 1, 1/2. And we know it goes like that, and we know it goes like that. It Tron cycles along the x-axis. And we can do the same thing for y equals 3 to the x. Again, 0, 1 is a point. Now we've got 1, 3, and negative 1, 1/3. And that's all you're really doing. All right. Let's explore that x minus h plus k thing. Let's do it with our 3 to the x. So let's look at f of x equals 3 to the x minus 2. So this, and this is effectively plus 0. hk is 2, 0. So our center shifts from 0, 1 to 2, 1. And that's all we're doing. And I wanted to make that an asymptote, and I didn't. One, two, three, 1, 2, 3. So 2, 1 is our new center. And it used to be this. So all of these shift right too. We can look at that here. And as we can see, the green is the x minus 2. It's just grabbed the graph and moved it right too. This is at some weird value right here. And it's 2 over here. Where's the next spot? It's a good spot to tell. 3 squared is at 9. Now we got 4 squared. Or not, I'm sorry. 3 squared is there, but when we plug in 3 to the 4th, now it's 3 to the 4 minus 2. It treats it like 3 squared. So when we have the h shifts the graph right. H units. Let's add some more to it. It's handy having this Desmos open. I'm really digging that. Let's throw a k in. I can't do this in class. I either have the projector or I don't. Here I can have Desmos up and right. So here h shifts it right twice. K equals negative 4. Move everything down 4. So it's handy to plot where everything was. We had, this is 3 to the x. And then we moved everything right 2 numbers. And now everything goes down 4. Including the asymptote. The asymptote was here. The asymptote shifts down 4 is right there. And we get y equals 3 to the x minus 2 power minus 4 does this. And it used to look like this. The minus 4 has moved it down k units. And we can see that here. We still have an asymptote. It's at -4. This value here dropped. 2, 1 dropped to 2, -3. Some fun stuff like that. So this one right here is f of x equals 3 to the x minus 2. This one right here is f of x equals 3 to the x minus 2 and then minus 4. What happens if we make it negative? What did the negative used to do before? It flipped the graph over, and that's what it's going to do. All of these points are going to reflect across the axis of symmetry. This one is 1, 2, 3 up, so we're going to go 1, 2, 3 down. Is that right? Look at that. It's exactly what happened. It reflects it across this axis of symmetry. And the closer we zoom in, we see that it stays that way. It's kind of neat. So f of x equals a to the x minus h plus k. 0, 1 moves to h k comma 1, or k plus 1. The asymptote goes from y equals 0 to y equals k. And if there's a negative out front, reflect it across the asymptote. And you will find this stuff tends to be easiest to do by graphing 0, 1, -1, 1 over a, and 1 comma a, and then making these translations. Move the points right h, move the points up k, or down if it's negative, and then apply any reflection that you need to. Now there's another exponential that shows up throughout nature. And let's take a look at it. F of x equals e to the x. E is like pi. It has a value. And it's a non-terminating value, non-repeating value. To a couple dozen places, e is approximately 2.71. And f of x equals e to the x shows up throughout nature. The COVID-19 graph you're seeing in the news starts off like this exponential function. But there's more to it that limits the growth. And eventually causes it to go back down. If I haven't linked it already in Canvas, I'll load up a document that shows how this works with COVID-19 using an exponential function. All right. Let's take a look at how can we solve these sorts of things. So let's look at f of x equals e to the x real quick. We have 2 to the x there, 3 to the x there. E to the x should be right between them, and it is. Let's make it green. And 2.71 is closer to 3, so the green line stays closer to the blue than the red. It's just another value. So let's look at solving exponential equations. Example, let's just dive into it. 5 to the x power equals 1 over 125. The way to solve these goes back to the a to the b equals a to the c if and only if b equals c. The idea is write both sides with the same base. All right. 1 over 125, 125 is 5 cubed. And if I move 5 cubed to the numerator, it becomes 5 to the negative 3. Now the bases match. The exponents have to match. That is an easy way to go about doing these. Pause the video for a second and work on that. Tinker around with it. And now I'm going to give you a couple to try. Let's take a look at 2 to the x equals 1 over 32. And then take a look at 3 to the x plus 1 equals 9 to the x minus 3. Pause the video and try to work those out. And remember, you're trying to get the same base. All right, I'll assume you paused. This one I can write as 1 over 2 to the 5th power, which means I have 2 to the x equals 2 to the negative 5. So x equals negative 5. Here, I can rewrite this as, well, 9 is 3 squared, right? And the rules with exponents is when we have a power on the inside, a power on the outside, we multiply the powers. So I've got 3 to the x plus 1 equals 3 to the 2 times x minus 3, which means x plus 1 has to equal 2 times x minus 3, and we solve. We distribute our 2. We'll gather the x's on one side and the constants on the other. And I get x equals 7. Not too bad, right? Another spot this shows up in is compound interest. So let's look at a compound interest problem. Compound interest. It follows the equation a equals p times 1 plus r over n to the n times t. A is the final amount. P is your principal or starting figure. R is the annual interest rate as a decimal. Don't leave it as a percent. You want it as a decimal. N is the number of times per year it's compounded. And T is the number of years. It's like time in years. That's why we use T. So that's the equation. So let's say, pause it if you need to write this stuff down. We're going to work on a problem. Let's say we invest $2,500 in a CD. CD stands for Certificate of Deposit. It's something banks do, where you guarantee to not draw out the money for a specific amount of time, and they guarantee to pay you an interest rate. Let's say they offer you 3% annual interest. That is compounded semi-annually. Semi-annually is not that good. But it's twice per year. If you never add any more money, how much will you have in 10 years? So go ahead and write that problem down. We'll do it together. Okay. So a good strategy for these things is write down the letters and figure out what they are. A is the amount, but it's the final amount. That's the thing we don't know right now, correct? The starting amount is the amount we invested, $2,500. The annual interest rate was 3%. In decimal form, it's 0.03. Compounded semi-annually is twice per year, n equals 2. And we said, how much will we have in 10 years? T equals 10. We have A equals 2,500 times 1 plus 0.03 over 2 times 2 times 10. This lines up with our A equals P 1 plus R over N to the NT. And this is just a matter of taking things slow and try to avoid rounding until the very end. So let's work through this. Uh, 0.03 divided by 2. So the 0.03 divided by 2 is 0.015. And I can do the 2 times 10 right now. That's 20 as well. And then I'll add inside the parentheses. I get 1.015 to the 20th power. What is that value? Let's do it in a calculator together. Oop. 1.015 raised to the 20th power. Now this is what I would do if I was showing my work for like an exam. But I'm not going to round this at all. I'm going to multiply by, take the answer, multiply it by 2,500. So there's no rounding whatsoever. 3367.137516. Now that we're done, now it's a good time to round. Money only goes to 2 decimal places. So we'll round to the 2nd decimal place. After 10 years, the 2,500 is grown to 3,367.14. How much interest did you make? Well, the idea is that if we have the principal and we add on the interest we make, we end up with the final amount. So we have 2,500 plus I equals 3,367.14. We solve for I by subtracting 2,500. And we get I equals $867.14. Why don't you try computing this same thing, but let's change the number of times it's compounded. What if it's compounded monthly? N equals 12. If it's compounded daily, N equals 365. You should go through and try working these out. Pause the video, go through this same process we did here, and figure out what the new amounts will be. If you pause it, I'll show you what the new amounts are. This one leads to A equals $3,373.38. This one leads to $3,374.61. What if we change the interest rate? Compounded semi-annually, but let's make the rate 4%. If you go through and do those calculations, ooh, it's raining. I'm glad I opened the window. I love listening to the rain. A equals $3,714.87. Now, what did we have up here? This was at 3%. This is at 4%. This is compounded twice a year. This is compounded daily. Compounding it daily only gave us $7 more. Adding just a single percent raised the final amount by 400. So the moral of that story, interest rate has a much bigger impact on final amount than the frequency it's compounded. I'll give you another one. So you have a child and you want to set up a savings account. Your child was just born. You want to set up a college savings account for your newborn child. Let's say you get a 6.5% interest rate, which is highly unlikely. That is compounded daily. You are anticipating a lawyer. So you want $400,000 when it's time for college. How much do you need to invest right now to have that much in 18 years? You actually have a little bit longer because they're not going to burn $400,000 up the very day they go to college. But let's just work out a problem like that. So let's identify what we know. I'll assume you paused the video and have written this down. Identify what you know. We've got A, P, R, and T. We go through the problem. It says we've got 6.5% interest rate, 0.065. Compounded daily, there are 365 days in a year. Let's ignore the fact that there's a leap year every 4 years. You want to end up with 400,000. That's our final value. And we want that in 18 years. Apparently, our variable here is P. So we set it up. 400,000 equals P to the 1 plus 0.065 divided by 365, all raised to the 365 times 18. So 0.065 divided by 365 equals. I'm going to add 1 to it. Then I'm going to raise that to an exponent. I'm going to put in parentheses 365 times 18 And that's what this is. That's this value right here. So I have 400,000 equals P times 3.22165735. We divide both sides by it. Blah, 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 blah. Don't round. I'm going to do what I'm going to do in my calculator. Most calculators will work like this. I'm going to say 400,000 divided by answer. And it tells me $124,159.71 is P. If I want to end up with 400,000 in the account and don't want to put another penny in it, and I get that good of a rate, I need to invest that now. Okay. There is one other form of problem, but they follow the exact same thing. And later on, we will do like a section that's all word problems on this stuff. But I want to show you the formula. It's continuously compounded interest. And rather, we had A equals P times 1 plus R over N to the NT. That's for non-continuous. When it goes to continuous, it shifts to PE to the RT. Where E is that value is a number. It's 2.71 to several decimal places lat. It's unending. A, P, R, and T are the same thing as before. So this is continuously compounded interest. This has a similar form. What we're seeing in the COVID-19 thing, there's a little more to it, but the base function is f of x equals e to the kt. T is time. K is exponential growth or decay. If k is greater than 0, we have growth. For k less than 0, we have decay. This is like a half-life of radioactive matter. And stuff like that. So there are problems that we will do in science and physics, and we'll even look at COVID-19 a little bit later with some data from March 30th. And that wraps up 4.2. I will get this uploaded soon. Peace.